Depth-first search and breadth-first search are the most common coding interview algorithms that you need to know. In many coding problems, you're required to traverse over each item in a tree or graph in order to perform some operations. This is where you need to use depth-first search or breadth-first search. These algorithms can seem a bit complex at first, especially if you're just starting out, but they can actually be quite simple to understand, especially when you approach them visually. In today's video, we are going to learn them with visualizations in a way that's easy to understand even if you're a beginner. Depth-first search is a more common algorithm in coding interviews than breadth-first search. It explores as far as possible along each branch before backtracking. Let's say we have a binary search tree of these elements. With depth-first search, we would start at root, which is 71. We go to its left subtree, which is with the root of 40. And we keep going to its left subtree until we reach the edge. In our case, it will be 14. And once we reach the edge, we come back to the root and start processing the right subtree. And we do this for right subtree as well until we reach the edge there. And we have three types of depth-first search algorithms. The one that we just saw is the in-order algorithm, where we visit the left subtree, then the root, then the right subtree. As you can see from the output, we get the items in this case in a sorted order. So in-order traversal retrieves elements in a sorted order. We also have the pre-ordered depth-first search, which visits the root node first, then the left subtree, and then the right subtree. With this algorithm, for example, we can recreate the same tree. It doesn't return the elements in the sorted order, but it returns in the same order as we have the tree in our case. And the third one is post-order traversal, where we visit the left subtree first, then the right subtree, and then the root at the end. You can easily visualize this if you think of each node as having a flag attached to it. In case of pre-order, the flag is attached from the left, and we need to collect the flags to traverse the tree. In case of the in-order, the flag is attached at the bottom, so we start from 1, 2, 3, 4, 5, 6, 7. And in case of post-order, the flag is attached on the right side. In terms of common usage, in-order is the often used one, because it retrieves elements in sorted order, which can be more useful than the post-order or the pre-order one. In any case, the time complexity for depth-first search is O of n, where n is the number of nodes, because each node is visited only once. And it uses O of h space complexity, where h is the height of the tree. This is because of the recursion stack that we are using. The actual code for this is very simple. In case of in-order traversal, once we have the root, we start processing the left side of the tree. Then we print or do whatever we want to with the root's value. And then we start processing the right side of the tree. And we have our base case where the root is not defined or it's null, which means that we reached to the edge. We just return out of the function. And the only difference between all three algorithms is just the order of the operations that we are doing. In case of pre-order, as the name suggests, we just do the printing before we start traversing left and right sides. And in case of post-order, we do that at the end. Common use cases of depth-first search are, for example, when we need to build a binary search tree from a sorted array or vice versa. With depth-first search, if the tree is binary search tree, we can loop with depth-first search and push the items into some array. So we will have the items in sorted order in our array. And we can also do the opposite, where we build a binary search tree from sorted array. It is also useful for checking if a tree is a binary search tree. Or path finding. For example, depth-first search is used to explore paths in a graph or tree, making it useful for finding a path between two nodes. It's often used in backtracking algorithms such as permutations and combinations, Sudoku solvers, and so on. The downside of depth-first search is that it can get slow if the tree is unbalanced. Another type of traversal algorithm is breadth-first search, which visits nodes level by level from the root downwards. So with breadth-first search, we would start at root, which is 46 here, and we add it to the queue. Then we start processing the nodes from the front of the queue. So we process the root, and we add its children 27 and 75 to the queue. On the next iteration, we process the node in front of the queue, which is 27, and we do the same for each node of the tree. So on next level, we would have 9, 32, 64, and 82 items. And then we continue processing the nodes until we reach the end where there is no more items left in our queue. The code of breadth-first search is usually written in iterative form, as recursion doesn't suit well with this algorithm, because it needs to remember where to go next after processing each layer. We need to keep the order in a queue data structure to track nodes. Each node is visited only once, therefore the algorithm complexity is O of n. And space complexity is also O of n, where n is the maximum width of the tree. Common use cases of breadth-first search are, for example, level order traversal in trees. It is the go-to algorithm for traversing a tree or graph level by level. It's often used to print all nodes of a tree at each level depth. It's ideal for finding the shortest path, as it explores all neighbors at their present depth level before moving to the next level. For example, in social networking applications, breadth-first search can be used to find people within a certain distance from a user, reflecting the friends of friends concept or nearby people in Messenger. It's also applied in games or puzzle solving, such as finding the minimum number of moves to solve a puzzle or to reach a particular state in a game. The downside of breadth-first search is that it requires more memory compared to depth-first search. I recommend you practice some LeetCode problems to familiarize yourself with depth-first search and breadth-first search algorithms, because they are the most common ones for interviews. I'll leave some problems in the description in case you want to check it out. Also check out the visualgo.net website, which has really nice demonstrations of depth-first search and breadth-first search algorithms. If you're interested more about the tree data structure on which we usually perform these algorithms, I recommend you check out this video next about most common tree types in coding interviews.